how about 10 degrees across Evap, but RLA is only at 45%? Now, this is in the context of a machine being loaded or not loaded, or the chiller being loaded or not loaded. And so I've recommended in the past that, basically for a chiller design for a 10 degree drop across the evaporator, if I am operating at that and I've got about, say, at least an 8 degree or more difference, like I'm making set point and I've got enough, my entering water is high enough to be 8 to 10 degrees, or at least 8 degrees above that, then I consider I've got a pretty decent load, and I should be able to get a pretty good analysis of how the chiller is operating. Now, that is in the context of I know for sure that my GPM is correct, my refrigerant charge is good, my tubes are good. Like, that's in the context of all these other variables that will impact that differential temperature, are in a good state, a good condition. Like, it's very, very important. So if we haven't verified that part, then using the temperature difference across there has a lot less value as a meaning, because if we're flowing too little GPM, like, that's going to completely change things. And we may not have a lot of load, but we'll be able to make 10 degrees really easy, because that water has so much contact time because it's flowing so slowly through the evaporator that we're able to make 10 degrees even though we don't actually have a lot of BTUs flowing through the chiller. Now, another thing I want to address here is you've got 10 degrees, but only 45%. So there's a couple of other things that, let's say all the other conditions are absolutely perfect. Okay, we know that our GPM, our charge, and our tubes, all of that is in good state. We have proper heat transfer. This condition can still happen, and it'd be perfectly normal, where we've got a 10 degree across but only our compressor is only pulling 45% RLA, which would mean that we've got a loaded machine, but yet our motor load is quite low. Well, there's two other things that affect this. It comes down to lowering lift. So I don't have that kind of data, but just things to consider. The lower we can maintain our lift through the across the compressor, and this is true for any compressor, okay? This isn't just a centrifugal thing, but the lower we can maintain that lift, then the less compression we're having to do. And the less compression we have to do means the less work we have to do to still move the same volume of BTUs. So what that could look like is, one, you may be running a higher chill water set point. So instead of 40, 42, 45 degrees, maybe you're running 48 or 50 degrees, depending on your application, or if you've got a temperature reset happening where maybe you've got lower load conditions, well, I guess this wouldn't be lower load, but just depending on your circumstances, you may have a higher chill water set point. That particular case, that raises the evaporator pressures and raises the saturation temperatures, which lowers the total lift the compressor is going to have to do. Because of that, we have less actual load on the compressor, because we don't have to compress as hard to get to our condenser saturation pressure that we need. Now, the other side of that too is, especially in a water-cooled environment, but even air-cooled ambient, we could significantly reduce our condenser water temperature, or allow our condenser head pressure to drop significantly if we're discussing air-cooled. So basically, if instead of allowing the fans to stage to maintain a higher head, we could just allow all the fans to stage on and drop our head significantly. Now, there's oil ramifications and stuff if we're not careful with this, but ultimately, if we get our condenser pressure down and our head pressure down, then again, we have to compress less. It's not as hard to get it from the evaporator to the condenser at the proper saturations. And if you combine both of those together, where you've got a higher evaporator set point and you've got a lower condenser water set point, the two of them are working together to lower that RLA that the motor is going to have. So you could still have a technical loaded condition and GPM and all that be fine, but still have a very minimal load on the actual motor of the compressor. And it's just because we're not having to go as far with it. If you're having to compress from 45 degrees of saturation to, say, 70 degrees of saturation versus 45 degrees to 100 degrees of saturation, that is a major difference in how much work that compressor has to do. Major difference, which is going to be reflected in your RLA. So RLA is not a matter of, is this compressor running at maximum load that it could possibly handle. It is how much work is it having to do to flow the volume it's being asked for at this time. That is how I would characterize what RLA is communicating. The compressor may be able to stage up more if it needed to, but if you're making set point, it doesn't need to, but because of our lift conditions, we just may not have it may not require as much work to get it there. So yeah, that would be my assessment if I had a condition where it would be what I would consider fairly loaded, a 10 degree and everything's correct in terms of design specs, but I've only got a 45%. I would say that we've got a full load, but we're managing our lift really, really well. And that is enabling a really low RLA, which is where you're maximizing the cost of performance, the COP. Like we've got a really good COP at that point, which is all part of why, like if we, in a water cooled environment, if we can get that head pressure down and keep our condenser water under control, like we can save a huge amount of efficiency. And I get, there are people who specialize in building optimization, and they're not necessarily mechanical HVAC experts, but they understand envelope and they're some level engineer, somebody. And I've had these arguments before where they're trying to sell the customer, our customer that we're working with, that they need to run higher condenser water set points in order to get the tower fans to not stage up as much and run more efficiently to save energy. What they do in the process, though, is by raising that condenser water set point, yes, we go from pulling 20 amps to 40, 50 amps on the motor, but our chiller in turn goes from doing 100 amps to 150, 200 amps instead, because where we could maintain really low condenser waters and maximize the chiller's efficiency, instead we are forcing the chiller to run at a much less efficient state by having higher condenser water, just so that we can save a few amps on the tower fan. Granted, those of us who have this, like we're on this side of things and we're looking at the bigger picture, that's easy to identify on our side, in my opinion. On their side, again, they're not looking at it from that perspective. So anyway, yes, that is, if you have that condition, that would be my thoughts around that. If you're not already in Chiller Academy, I'd really encourage you to go check it out. Just think about it, right? This is what I do full time. I've committed. I've stepped out of the field, committed my career to this going forward. This is what I've always wanted to do, and to be able to educate, help others, and grow, and help this industry take steps forward. So chilleracademy.com. Like I'd love to be able to work with you over there. We've got a community page. All the lessons have a comment section. That's what I spend a lot of my day doing. If I'm not working on the lesson material itself, then I am in the comments and I'm trying to respond to those as fast as I can, in addition to helping you through email and otherwise. So, love to be able to work with you. For all of those that are in the academy, y'all are doing some great work out there. Keep it up. I really appreciate the support and the feedback that you've given.